Okay, some of you may have already done Descartes' rule of signs. If you're getting it already, you can skip this first part of the screencast. But this is kind of a strange thing we do. It's something that was Descartes came up with, and before calculators, it was pretty helpful. Now that we have calculators, this isn't the most helpful theorem around. But we are going to go over it, and there are some nice things about this theorem. So give us the number of possible positive real zeros. So what we're talking about here is positive real zeros. So you have to kind of first understand what we're talking about with positive real zeros. So let's talk about two different graphs here. Let's say we have this graph and it does this. Well, this is what I would call a negative real zero right there. The x value is negative, so it's called a negative real zero. These two solutions on this side are positive real zeros because x is positive to the right of the origin. And so this would be the number of, you would have two positive real zeros for this graph. If you had a graph like this has a negative real zero, but it has zero positive real zeros. So Descartes' rule of signs can tell us, first of all, the possible number, and I say the word possible, of positive real zeros is either equal to the number of variations. So what in the world does it mean by number of variations? So if you have a function, the variation sign is when you change from negative to positive. In this case, we change from negative to positive, from one term to the next, from positive to negative. That's a change in sign, so another one. And from negative to positive, well, that's another change in sign. If it stayed the same sign, you wouldn't add one here. And another change in sign. So we had 4 sign changes. So I'm going to write 4 positive real zeros. This tells us the number of positive by the number of variations. So there are 4 positive, or, oh, this is an interesting statement, less than that by an even number. Well, 2 is an even number. So what's 2 less than 4? Well, that would be 2. Well, 2 is an even number. What's 2 less than 2 is 0, and I can stop at 0. So there are actually 3 possibilities, 4, 2, or 0 positive real zeros. I don't know how many there are, so I know the graph either looks something like this, maybe, where it crosses the x-axis in the positive side 4 times. Or maybe the graph looks something like this, where it crosses the x-axis on the positive side 2 times. Or maybe the graph looks something like that, where it doesn't cross the x-axis on the positive sign at all. So one of those 3 types of graphs where you're trying to figure out how many times could it cross. And so we know it doesn't do this. Like, we know it doesn't just barely touch and only touch in one spot. That's not a possibility. The reason is 1 is not one of our possibilities. So it has limited our choices somewhat. Number of negative real zeros. So now we can tell about the negative real zeros by plugging in negative x. It says plug in negative x. So if I plug in negative x here, I get negative x to the 5th plus 8 times negative x to the 3rd minus 9 times negative x squared plus 3 times negative x minus 2. So now, kind of like we did with some of the other times we do that, is this always positive or always negative? If you look at just this part of this, the negative x to the 5th here, you've really got, that's always going to be negative, right? Because a negative to an odd power is going to be negative. So I have 4x to the 5th minus or plus, let's see what happens here. I should just wait on the plus or minus here. Let's actually look at it first. So look at this term. You can see the negative to a 3rd power will always be negative, so I am going to put a minus there, minus 8x cubed. And let's look at this. So if you look at just this part of the term there, A negative squared is going to be positive, so this is still negative, so I say minus 9 x squared. And then if you look at this term, negative x, that's always going to be negative, so I'm going to say minus 3x and then minus 2. So once you do that, now we're going to count the number of sign changes. So from positive to negative, that's one sign change. From negative to negative, no sign change there. Negative to negative, no sign change, no sign change. So there's only one negative real zero. Now it says or less than that by an even number. Well, if I subtract 2 from 1, I get negative 1, and that's no good. There's really no sense in figuring out. There's no negative numbers of real zeros. You could have 0 at the least, and then you could have a maximum of 1 in this case. So you actually have just 1. This is the only possibility of negative real zeros. So I know something about the graph. I don't know exactly what the graph looks like, but I do know that whatever it looks like, it only crosses the positive part of the x-axis right here in one spot. That is something I know for sure from the Descartes rule of signs. Let's kind of put this together with the first answer we had. We had there were 4, 2, or 0 positive real zeros, which we got on the last page. So let's think about how many real zeros this function will have. So if you look at the first term, you can see that it's definitely going to have 5 zeros for sure. I know this one's a given, right? There's no doubt that there's one negative real zero. So there must be 4 other zeros somewhere. Well, one possibility is you have one negative and then you have 4 positive real zeros. If that's the case, the complex, or we might call them imaginary zeros, if there's one of these and 4 of those, that would mean that takes all 5 of them. There would be 0 imaginary zeros. But there's another possibility. What if there's one negative real? I know there is. And maybe 2, that's one of my possibilities for positive real zeros. 1 plus 2 is 3. That's a total of 3 zeros. Well, I know there are 5 zeros, so there's 2 missing. So that's another possibility. There could be 2 imaginary numbers here, imaginary solutions. And the other possibility is 1 and 0. If that's the case, there would be 4 left over, so there could be 4 imaginaries. Now the thing about these imaginaries, again, they only come in pairs, so you'll never see an odd number of imaginary roots. They go to the mall together, they look alike, they travel together, so they always come in pairs. So it could be 4, 2, or 0. I don't know how many. Those are all my possibilities for the types of zeros that I'll have. So Descartes' rule of signs really just kind of tells us a little bit about the possible number of roots you could have. Let's just look at one problem here where we can find all the zeros. So again, it's to the 3rd power, and I should probably have f of x here or something like that. But the function starts with the 3rd power, so I've told you that you can find one of the roots from the calculator. So I recommend just go ahead and bring up a calculator, and we're going to type in x to the 3rd power minus 7x squared plus 17x minus 15. If I graph that, you can see that it definitely does cross once. I guess if you perform a trace, if you're not sure, I'm typing 3, and it looks like 3 is indeed, I'm going to lay a point down there, 3 is indeed a solution. You can see right there. So by the way, I could also list out the solutions. Remember what we did the other day, factors of 15 divided by factors of 1. So 15, 5, 3, and 1 all over 1. So my possible rational zeros, 1 is the first coefficient, factors are only factors with 1. So plus or minus 15, plus or minus 5, plus or minus 3, and plus or minus 1. There really is, so one of those is the solution, 3 is, and so I'm going to synthetically divide out a 3. Use synthetic division, 1, -7, 17, -15. So if I bring that down, 1 times 3 is 3, I get -4. I know my remainder is going to be 0 here because I see that it's a root. 3 times -4 is -12. That helps sometimes because it's easy to make a mistake. 3 times 5 is 15. Whew. Got a remainder 0. And so then I might want to put in, this is a constant, this is an x term, and this is an x squared term. And this problem's, it gets a little bit intense, but all this is one of our factors, right? We have a factor of x squared minus 4x plus 5. I know it's a factor because the remainder is 0. There's actually another factor, it's kind of hidden, but 3 is a solution, so I know that x minus 3 is a factor. That's the factored form of the polynomial above. And so the solution, of course, is x equals 3. Well, we got that one from the graph right here. And then guess what we're going to have to do here? Unless it factors, let's see if it factors. Factors of 5 that add to 4, almost, but I don't see that. So at this point, I would apply the quadratic formula. Negative b would be 4 over 2 times 1, plus or minus b squared, which in this case would be 4 squared is 16, minus 4 times 1 times 5. Well, 4 over 2 is just 2, plus or minus square root of -4, which is really 2 plus or minus 2i over 2. Of course, the 2's cancel, and you get 2 plus or minus I as your two imaginary solutions, and of course the other solution was 3. And so we have 3 solution, it's x to the 3rd power. I know I found all my solutions, and that is the end of the screencast. I think you can do the lesson now.